Hello, let us start the next lecture of week 10. In this week, we have been talking to you about the use of nanomaterials for energy applications. In the first two lectures, we gave you an overview of the areas, primarily energy areas, where nanomaterials are being utilized. In the previous lecture, I talked mostly on batteries, more so on secondary batteries. There is another very important area where nanomaterials are being utilized, and that is supercapacitors. In this week, we will start with the use of nanomaterials. As I have said, we will talk about the utilization of energy generation unit for direct applications. We have also introduced the concept of intermittent character of the renewable based energy generation units, which are driving the necessity to have efficient energy storage technologies. We have talked to you about batteries, and batteries are high energy density systems. That means they can give you constant energy over a long period of time. But there are applications where you need burst of energies, that means huge amount of energy, but for short period of time. This is actually being catered by the device which is called as supercapacitors. So, we will talk to you about the supercapacitors in this week. We will start with the basics of supercapacitors, then we will talk to you about the classifications of supercapacitors. How does the structure of a supercapacitor varies from that which we know, that is conventional parallel plate capacitors. That needs to be understood. So, we will talk about the device architectures. Why do you see such high capacities in such devices? For example, in conventional capacitors, you were talking about millifarads range, but in supercapacitors, you are talking about from tens of farads to hundreds of farads. So, it is not just few times increase, it is few orders of magnitude higher capacities which you get in such devices. This has been modeled using various theoretical models, and we will introduce some of them today. We will also give you some basic introduction towards the characterization tools used to investigate the properties of supercapacitors, mostly cyclic voltammetry, the charge discharge studies, and electrochemical impedance spectroscopy. In the previous week, we had seen that porous materials can be extremely useful for various applications. We must see whether porous materials can also be used in devices such as supercapacitors. We will talk about that concept, and finally, we will discuss some of the materials which are routinely used in these devices. If you look into the supercapacitor, it is basically an energy storage device that stores large amount of charge through the electrostatic separation at the electrode electrolyte interface linked to either charge separation at the interface or fast surface redox reactions near the interface. Clearly, these two ideas are seemingly different, and that is where the classifications of supercapacitors comes. You will see that we classify supercapacitors in one case where parallel plate capacitance is being simulated by charge separation near the interface, that is you do not have any Faraday reactions taking place. So, those are coming as electric double layer capacitors, but where you are seeing Faraday reactions, that means you can have redox reactions near the interface, those are classified as pseudo capacitors. And these supercapacitors bridge the gap between conventional capacitors and batteries in terms of energy and power densities. As their charge discharge process is highly reversible, it enables these devices to have long cycle life with very limited capacity fading. So, you can have highly efficient storage mechanisms and you can also have long cycle lives. We are talking about few hundreds of thousands. So, if you look into a supercapacitor, it actually has again just like a battery various components. Let us say we talk about a coin cell. So, you have this coin cell which has a negative casing on the top, a cathode material, a separator, an anodic spacer, a conical spring and a positive casing. Each one of them have a particular role to play. So, now you can see these are acting as charge collectors. Spring is used to maintain pressure between the anode and the cathode, so that you have the structure being maintained and you do not see variation in the D spacing. Separator is again an ion conducting membrane. Cathode and anodes are the materials where the positive or negative charges will get stored, or you will have an layer forming near these structures and charge balancing can take place. So, if you look into a pseudo capacitor, there you will find that Faraday type reactions take place in contrast to electric double layer capacitors, where no charge exchange takes place and you only have the formation of parallel layer of charges near the cathode or anode. So, these two are the basic classifications of supercapacitors. One is electric double layer type capacitors, others are pseudo capacitors. Now, you have a third category that is called as hybrid supercapacitors. There the advantages of EDLCs and pseudocapacitors are coupled so as to increase the capacities. So, you have one of the electrodes as EDLC type electrode, where the other is a pseudocapacitive electrode. So, what happens in pseudocapacitor or EDLC? Let us first understand. I had discussed this in the previous lecture, but let us also repeat that concept today. So, you have two electrodes in conventional capacitors. Now, suppose you have nanomaterials which are there. So, now on a current collector, now let us say this is a metallic plate where there is a current which is acting as a current collector. You deposit these nanomaterials. So, you coat these nanomaterials. These nanomaterials have very high specific surface area. Meaning that you have lot of active sites near the surface. We know that C is equal to K epsilon naught A by D, where A is the area of the electrode plate, D is the separation between the two plates, epsilon naught is the permittivity of free space, and K is the dielectric constant of the electrolyte in this case or dielectric medium. Now, when you have such nano material, then what is happening? If when you apply a potential, then one side gets positively charged and the other side gets negatively charged. Now, there is an electrolyte in between which forms a, for example, a positive core surrounded by water molecules, if you are talking about aqueous electrolyte. So, this forms a solvated ion. Then you have negative core with water molecules around it, that is an aqueous electrolyte. The positive and negative ions are in a solution form in water. So, now you have a negative core surrounded by water molecules and you have a positive core surrounded by water molecules. So, you have now when you have let us say a negative charge on this side, what will happen? It will attract the positive ions to move in this direction. So, positive ions will start moving in this direction and vice versa on the other side. So, now what will happen on this structure? You will have formation of the positive ion and on this side you will have the layer formation by the negative solvated ions. Now, if you look into conventional capacitors, area was, let us say, 5 centimeter square or even 10 centimeter square, conventional capacitors. But here these nanomaterials are giving you specific surface area in the range of, let us say, 500 meter square per gram. So, if we want to even say that we want to compare in terms of centimeters, let us say we are getting somewhere around 1000 centimeter square per gram, just for comparison. Then you can see you have nearly 3 orders higher area for charge accumulation, and hence A is extremely large. Now, this layer which forms, so if I simulate this, and this is conventional capacitors. What is the value of D? D is the distance between the two charged layers. So, what will happen? What will be the D value here? The D value here would be this, the distance between the positively charged layer and the negatively charged layer on this side, and vice versa on the other side. So, D is extremely small because these, let us say, are in the range of 10 nanometers or so, because size of the solvated ions are also quite small, let us say around 2 to 3 nanometers, and then you have these layers forming and the value of D actually decreases. In supercaps, in aqueous based systems, there is, when you have a water based electrolyte, sometimes there is also an adsorbed water on the surface. So, there can be slightly larger value of D because then there would be some adsorbed water and then the layer formation, which is a distance D. So, effective D would be D plus D thickness of the adsorbed water layer, but for the time being, let us say we consider only these two layers. So, D becomes extremely small. For example, here you had distances, let us say 1 millimeter, 10 raised to the power of minus 3, and here you are talking about 10 raised to the power of minus 8 if you have 10 nanometers. So, that basically becomes approximately 10 raised to minus 8 meters in this case. So, now D has become very small, area has become large. So, what will happen to the value of C? C will become extremely high. So, just by changing the architecture slightly and using nanomaterials in place of bulk, what are you able to achieve? You are able to achieve very high capacitances. You do not get full increase because you will have some layers of nanomaterials where the ions may not be able to intercalate, and the value of D may be slightly larger than what you expect theoretically. But even if we just want to see a typical increase, the increase would be of the order of 5 to 6 times, and therefore, you can easily move from millifarad range, which is obtained in capacitors, those are conventional capacitors, parallel plate capacitors, to few farads to hundreds of farads. So, for the same capacity, you can easily reduce the size of the capacitor, increase the power density of the capacitor, and because these are highly reversible processes, you can have extremely high capacitances. These kind of charge separation based systems are called as electric double layer capacitors, because two layers form near the interface. So, here there is no charge transfer, but there is another example where you can have pseudo capacitor. Pseudo means it appears to be, where you use materials, nanomaterials based on mostly transition metal oxides or even conducting polymers, where there can be some charge transfer at the interface and the material can change its electronic state, resulting in the charge storage. Because of this, what do you get? Because of this changing state of the material, for example, if you use copper oxide or tin oxide, it can have various valencies and they can move from one valency to the other. If you use manganese oxide, it can go from 2 state, 3 state or 4 state and toggle between each other, and then you can store charges. There is a change in the potential. So, you have dq by dV that has the dimensions of capacitors or capacity or capacitance, and therefore, you call these systems as pseudo capacitors, because they give you a parameter which has the dimensions of capacitance, and therefore, these devices are called as pseudo capacitors. Here also, higher is the area where such charge exchange can take place, higher would be the storage capacities, and during discharge the ion will again go to its initial electronic state and release the electron, which would then flow through the external circuit, and the electrolyte will go back to the charge neutral condition from one end to the other. So, you have pseudo capacitance coming into picture. So, pseudo capacitors have higher capacitance than EDLCs, but because there is a continuous change in the material, the degradation of material is slightly higher in pseudo capacitors than in EDLCs. So, now you have two systems, EDLCs and pseudo capacitors. If you want to have advantages of both coupled together, then you make a hybrid system which takes one electrode as the EDLC type and the second as the pseudo capacitor type. So, schematically, if you look into what we have discussed just now, you will see this is what we are talking about. You have a current collector, an active material, a layer forming, so a double layer forming, so you call it as electric double layer capacitors. One side it is the positive charge accumulation from the electrolyte, so the solvated ions coming in from the electrolyte. For example, you can have acidic, basic or neutral electrolyte. You can have a neutral electrolyte like NaCl, and so Na plus will move in one direction, Cl minus solvated ions will move in the opposite direction, get accumulated near the interface near the electrode material, form a double layer and give you a capacitor like behavior. So, That is the typical construction of a EDLC type system. If you look into the theoretical model to what we have discussed, there are various models which have been proposed. Helmholtz first proposed the model where it was considered that ions are rigid point charge, where the thermal motion, diffusion were ignored. So, you had ions as rigid charges. So, this can only happen when you have very highly concentrated electrolytes, and then once you apply a potential, they go and form a double layer near the interface. So, if you have electrolytes more than 1 molar concentration, then you can use the Helmholtz model. But once you start using low concentration electrolytes, or even you start considering that ions are in reality not point charges and neither are they static. So, there is a diffusion, there are other features which will come into picture, and you will have like scan rate dependent behavior or current density dependent behaviors. Those could not be explained using the Helmholtz model. So, the Guy-Chapman model came in and realized that the potential decreases exponentially as the distance from the electrode increases. So, as you move away from the electrode, so as you move away from the electrode, then the potential decreases. So, this is decreasing as you move away from the electrode. The theory thus gives the production of ions. This prediction says that there would be diffusion into the bulk electrolyte, so that the overall charge of the electrolyte is neutral. But this was an over assumption of the ionic concentration near the electrodes, and it was still that point like ions were being considered, which again limited the explanation of features. Then came the Stern model. It actually combined the theories of Helmholtz and Guy-Chapman model and said that the electric double layer can be divided into two regions. One is the Helmholtz layer, where ions are specifically adsorbed. So, you had the adsorption, and second was the Guy-Chapman layer, where you saw there is a diffusion, that is ions are distributed according to the Boltzmann statistics, and you have diffusion of ions taking place in that model, and this gave the best description of the supercapacitive behavior. Next, which we had discussed was pseudocapacitors. Now, if you look into pseudocapacitors, here the redox reactions take place. So, what happens if you look into the metal or a material which is coming in from transition elements, then you can have either systems which would have the capacity to give electron or the capacity to take in electron and change its oxidation state. So, you have transition elements taking part in this. So, it was basically the change in the state. Now, if you are giving electron or taking out electron, means giving electron extraction of electron. So, you have the discharge process. If you put an electron, then it is a storage mechanism. So, that actually gives you the capacity to either store or take electrons out of these materials. Now, as it involves the chemical changes of the state of the reactant species, it results in electrons getting in or coming out, that means electron transfer. So, this gives you change in the value of Q, that is charge acceptance, that is delta Q, and because of charge going in or coming out, there is a change in potential, that is given by delta V. Now, dq by dV has the dimensions of capacitance, and therefore, it appears to be as if there is a capacitor being formed near these surfaces. So, you have the electrolyte, when it moves, reaches near the interface, it drives electron transfer or release or acceptance, and that is then utilized as a capacitor like behavior. If you look into the thermodynamic point of view, you will find that you can write the parameter y as the charge which passes across the double layer, and you have to relate it with the potential. So, now you can write the relationship between the quantity y and the potential which gets formed, and each of these can drive an electron transfer process between the oxidized species or the reduced species, and that is you can have the number of electrons either released or accepted. So, when you differentiate this equation, you will get dy by dV given by equation number 3. So, now you have a relation between dy by dV, and you will find that y is proportional to the charge which passes in each of the process, that is oxidation or reduction. Therefore, what happens? Pseudo capacitor will have the maximum at the half conversion of the redox pair or half occupancy of the surface of the bulk host, that is theta is equal to half or x is equal to half. Hence, the achievable capacitances are extremely large. Pseudocapacitors can further be subdivided as adsorption pseudocapacitors, redox pseudocapacitors, or intercalation pseudocapacitors. So, if you have intercalation pseudocapacitors, you are using more so layered structures which also facilitate intercalation of electrolyte ion within its bulk, and you have access to even larger area for undergoing redox reactions. Redox supercapacitors or pseudocapacitors are involving the electron transfer between the electrode and electrolyte species near the interface, and absorption pseudocapacitors, it is mostly coming in from the adsorption of electrolyte ions at the electrode surface. And as I said, you have hybrid supercapacitors which are a combination of EDLC and pseudo capacitor type electrodes. If you have both the electrodes made up of same material, it is called as symmetric supercapacitors, and if you have the two electrodes made up of dissimilar materials, then they are called as asymmetric supercapacitors. So, you can have symmetric EDLCs, asymmetric EDLCs, you can have symmetric pseudocapacitors, asymmetric supercapacitors, and hybrid type supercapacitors are predominantly asymmetric supercapacitors. Let us see some of the techniques which are used to characterize such supercaps. You have cyclic voltammetry and galvanostatic charge discharge. In CV, you actually record the current response to a linearly varying potential, and that gives you the charge storage capacity of the device. If you see CV curves of EDLCs, you will get a square shape behavior, whereas in pseudocapacitors there is a deviation from square wave or square shaped system. Why? Because you have a continuous occurrence of oxidation and reduction reactions which can impact the overall shape of the. If you look into the measurement techniques which are used, you have cyclic voltammetry and galvanostatic charge discharge processes. CV records the response of current to a linearly varying voltage profile, and that gives you the charge storage capacity. In EDLC, you have a square or nearly square shaped IV curve, whereas there is a deviation from a square shaped curve when you are talking about pseudocapacitance, because in pseudocapacitor you have redox and oxidation processes which occur over a range, and that modifies the shape of the curve. Similarly, you have the charge discharge profiles which are extremely important when you are talking about the application of these devices. Please remember, when you talk about the storage capacities, you always talk about the discharge curve and not the charging side of the curve, because we know in capacitors what do you get? If you have the curve, then you get triangular shapes, but this side is charging side and this side is the discharging side. The energy which is useful to us is the discharge cycle, because if I take, let us say, an hour to charge a capacitor and then it discharges in 1 minute, then it has practically no storage capacity. Please remember, we are talking about energy storage devices. Hence, it is the discharge curve which plays an important role. But because there are internal resistances which are taking care or are being impacted by interfacial phenomena, or because of the defects which come into the electrode material over a period of time, or you may not have an ideal electrolyte interface, or you have continuous degradation of the electrolyte itself, or you can have the deposition of the active material on the current collectors which is not giving you the desired impedance matching, that results in the drop of the voltage, and that is called as internal resistance. And if you see that kind of curves, you will see in the discharge cycle there is a immediate drop of certain voltage before you start getting the triangular wave back, and this drop in voltage is called as the voltage because of the internal resistance, and you can have the measurements of CD, which can give you the value of ESR, and electrode kinetics, which will give you the value of IR drop. So, if you see the cyclic voltammetry, then you have the typical values which are obtained from a area under the curve. Sometimes when you use softwares, you get such kind of parameters, but please note they have no physical significance, because they have, you cannot go to such high precisions. So, when you have values coming out directly from a software, please be very careful that you truncate these values to the instruments least count, so that you have a significant figure. Otherwise, if you just take what you get from the software, it may not have the real value. So, you can change the scan rate. So, you can change the rate at which you are scanning the potential window, and you can get the IV curve which is associated, and you can then get the area under the curve, which gives you the capacity of storage. If you want to use the formula for specific capacitance, where with respect to the kind of material you have used, the active material, then it is given by this formula, where which is 1 by MSR delta V from minus V to plus V I dV, where CV is the specific capacitance, mass is the mass of the active electrode material, SR is the scan rate, this is the operating potential window, I is the measured current, and IdV integration is the area under the IV curve. Similarly, you have from CD, as I said, this is the charging cycle, this is a discharging cycle, this is your voltage window, and this is your IR drop. So, you have IR drop. So, effectively you lose that amount of voltage. So, now you will calculate the area under the curve from this point, and then you will get the storage capacity. So, for that you use the formula CCD is equal to IDT M V minus IR, where IR is the drop in the voltage. So, if you have an IR of, let us say 0.2 volts and you have charged the capacitance to 1 volt, then effectively your voltage would be 0.8 volts, because you are losing 0.2 volt after the charging cycle. So, what is the contribution of nanomaterials in supercapacitors? Advantages comes in because the surface to volume ratio increases, the transport length of both mass and charges decreases, surface area decreases, low density, low cost, and you have low weight. We had talked about the porous structures. So, you can also tune the porous architecture in these materials. So, if you look into an electrode which seemingly is solid, but when you take a high resolution picture, it may actually have a porous channels that would allow the electrolyte ions to go in and then interact with the atoms within the bulk of this material. So, you have even higher accessible area for undergoing the charge accumulation or charge exchange, or and that gives you the higher storage capacities, and that is what you get. So, if you do not have these storage capacities, only the interface would be formed, but if you have porosities, then you have even higher accessible areas and you have increase in the overall area, which we have already seen that the surface to volume ratios can be very high when we are talking about the spherical particles. And then you tune the nanomaterial morphology, you change their shape, size, structure and atomic arrangements, and you can get new materials, new response characteristics. You change the transition metals, you get new response characteristics. You even modify the carbon electrodes which are used in EDLCs, you get new response characteristics. These are some of the carbon based materials which are used in EDLCs. For example, activated carbon, carbon nanosphere, you have even smaller size carbon nanospheres, you have graphene oxide, or you can have reduced graphene oxide. Clearly, you can see that their architecture are different, therefore, their surface areas are different, and hence what you will get, the surface to volume ratios would be different, and therefore, their reaction kinetics at the interface would be different. So, their stabilities are different, their mechanical stabilities are different. So, based on the requirement of the end user, you will choose the relevant architecture which gives you the desired output. You measure the specific surface area using the Brunner-Emmett-Teller technique, and you can get as a function of changing morphologies. For example, activated carbons can have specific surface areas in the range of 900 or more meter square per gram, and graphene quantum dots can have 73 meter square per gram. You can have nanospheres of carbon 51 meter square per gram specific surface area, or you can have graphene oxide which has a different morphology, but still gives you similar surface area. So, you have to choose these materials depending upon your requirement. This technique we will talk in detail in the next week. You can also measure the pore size distributions and pore radius. So, you can clearly see that you can tune the pore radius itself. So, the size of the pores also change, and therefore, the capacity of the electrolyte ions to intercalate also varies as you move from one structure to the other, and therefore, your storage capacities also change. As expected, you then measure the CV or CD curves of these materials. For example, let us compare activated carbon with graphene oxide. You can clearly see by the scales that their natures are very different as a function of applied current density or scan rates, and their areas under the curves are also different, therefore, their specific capacitances are also different. So, clearly you have a device which can give you high power density, you can get n number of supercapacitors routinely. What you need to do? You have to make new nanomaterial, and then you have to arrange them in the configurations which we have discussed. So, as your capacity to make newer and newer nanomaterials increase, you can easily make such devices which are now being used in your mobile phones to automobiles, from Formula 1 cars to railway engines for ignition, for in mobile phones for flash. You have regenerated braking coming in automobiles, or in Formula 1s you have high power being delivered in the DRS systems. So, you have large applications of these supercapacitors, and most of the energy landscape today, what we are talking about, will have a coupled system based on supercaps and batteries put together, and they are all dependent on the use of nanomaterials. If you do not use nanomaterials, these systems will fall apart. These are some of the references which are very useful, and you can go through them for even more understanding. So, I thank you for attending lecture 3 of week 10. Thank you very much.